Hello students, in this video I will be discussing about the circuit topologies that are used for increasing the op-amp's gain. Okay. So as we know that for lower technology nodes the length of the channel is small, and due to which the value of uh, R naught is basically small, and in turn it impacts the gain of the differential amplifier that we have discussed earlier, and due to which we are in need of some sort of circuit topologies that could enhance the gain to a large quantity, and that is what we are going to discuss in this coming set of series of videos. So now today I will be addressing one such configuration circuit topology, which is known as telescopic. But before I try to deal with these kind of topics, I just want to make some sort of a review on what we have done, and just to have some sort of grip on what we are about to discuss in the coming sessions. So I just want to bring out some of the commonly used differential amplifiers, and we'll just try to address two important parameters. One is the gain of the op amp or the differential amplifier, as well as the output swing. So these are the two major parameters that we will do right now with respect to a simple structure, and later we'll just move on to different circuit topologies. And one such topology that we are about to discuss in this particular video would be a telescopic op amp. Yeah. So without further ado, let me just try to bring out some of the structures from a different source. Let me try to grab a picture of those. Yeah. Yeah. So what are the structure that has been pasted here is basically known as a differential pair. With something known as a differential output. Yeah. So the reason why it is specifically labeled as a differential output is that you could able to see that the outputs are taken differentially. Okay. So that is the literal meaning of it. And let us right now focus on first across the gain of both the circuits of A and B, as well as the second parameter, which is going to be the output swing parameter. Yeah. So first let us talk about the gain of the circuit number A. So with respect to figure A, the gain, and as you could able to see that the circuit is completely symmetric, which means that one could draw a line of symmetry across this and take only one half of the circuit to analyze the gain of this, or the differential gain of this particular circuit, right. So we have already discussed about all these parameters. So in short, when we try to calculate the GM of this entire circuit, we would end up having a parameter value which is GM1, 2, and the output impedance computation. So probably I have to, yeah. So the output impedance calculation is done across this node V out, and when we look up, we basically have a diode connected configuration, and we know that this diode connected configuration has an impedance which is 1 by GM3 in parallel with RO3, and when we look down, we are looking into the drain and of M1, which is basically leads to a resistance, a small signal resistance value of RO1. Yeah. So obviously when the circuit is symmetric, we know that this node, which is basically the node which is labeled as VP, will be driven to the ground. Okay. So this is something that I forgot to mention. Yeah. So basically this node is at the ground, and what we have is basically a ground at the source of M1 when we apply a differential input across these terminals. Yeah. So having got this as our gain, let us move on to the gain expression for the second structure. So this is with respect to circuit B, and again, since the circuit is symmetric, one could draw a line of symmetry across it, and again the node at this particular node point is basically is equal to 0 when we apply an anti-symmetrical input, and due to which one could analyze only half of the circuit, and it's nothing but a CS amplifier with a current source load, and again the gain could be expressed as the GM of M1 and M2 into the output impedance. Again the output impedance, when we look up, we are looking into the drain of this M3, so that gives us an impedance value of RO3, a small signal impedance of RO3, and when we look down, we end up having a small signal impedance value of RO1. Yeah. So now that we have spoken about the first parameter, which is the gain, and the next thing is that we just talk about the output swing parameter. Yeah. So basically one could write the output swing parameter as something a VO max minus VO minimum. Okay, so generally it will have something like VO max. It is composed of two parameters further, or two different terms or parameters like VO max and VO minimum. So one has to compute these things in order to evaluate the total output swing out of the circuit. Yeah. So before I try to complete this output swing formulae, I just try to talk about this maximum swing and the minimum swing that I can have across the node V out, okay, or a particular node of this V out. Now let me choose a different. Yeah. So we know that there is a DC condition, or there is a Q point that is defined at this particular output, and which is basically defined as VDD minus VGS3. So it's all been discussed earlier. So I'm just telling you that there is a kind of DC condition or the DC value that exists across this particular node, and over this DC value there will be an output swing when we apply a differential swing across the input, right? Yeah. So in such a way that when there is an output swing that is happening around this DC Q point at the output, what happens is that the output swing generally tries to push or try to reduce the value of this VGS. Now what is the minimum value that one could have across this VGS would define as the maximum swing that I can have across, yeah, so maximum swing that we can have such that the transistor M3 stays in the saturation regime. Yeah. So we know that when we have a diode connected configuration, we know that the diode connected structure in general will have only two regions of operation, right? And the way that one could relate the two regions of operation is basically by looking at the current. Okay, so the other way of looking at which region this diode connected configuration works is by looking at the current value, and let us try to map these things. Okay, so those two different regions of operation are basically the cutoff. The other region of operation is basically the saturation. Okay, so these are the two regions. But whereas when you take a simple NMOS structure, okay, where there is no diode connected configuration, then this kind of structure will have three regions of operation. Okay, so these are some of the things that we have already discussed, and I'm just trying to concentrate on this diode connected configuration in order to get the value of this maximum swing. Okay, yeah. So now since because whenever there is an output swing, we want to make this M3 to stay in the saturation regime, we need to know what is the limit that I can have across this VGS of this M3 such that still I am inside the saturation regime without entering into this cutoff. Okay, so the way that one could distinguish the two regions of operation is, as I said, it's by looking at the current, right? So whenever this current ID that is flowing through this M3 becomes equal to 0, we mean that this transistor is in cutoff, and whenever it turns out to be a non-zero value, so whenever there exists some sort of current, then obviously it will be in the saturation regime. Yeah. So now in order to have this non-zero factor, what is the minimum value that we can have across this VGS, and that value turns out to be VTH. Okay, so that is the minimum voltage that we need to apply across the gate and the source of M3 such that still there exists a finite amount of current, not exactly equal to 0, but there exists a finite amount of current that flows through the circuit, and in a way the transistor is operated in the saturation regime. Okay, so due to which one could write that the potential when there is an output swing, so probably I will just take off some of the spaces here. So whenever there exists an output swing where there is a common DC condition at the output, and this common DC condition is written as VDD minus the VGS3, just because I am just putting a model just because it's a PMOS device, and the VGS value of this PMOS device will be a negative value. Okay, so due to which we have to apply this negative modulus across this VGS value. Yeah, so this is a DC condition, and over which there is a swing that is happening, and the maximum swing that it can go up would then obviously reduces the value of this VGS across this particular point. Okay, so now what is the minimum that it can have such that still our M3 stays in the saturation regime, and that value turns out to be equal to VDD minus the threshold voltage of this transistor M3. Okay, yeah. So this is how one could evaluate the VO max condition. So which I can write it as VDD minus the threshold voltage of this transistor 3. Yeah. So now let us talk about the lower swing. That is, what is the minimum swing that we can have around this same Q point. Okay. So what is the minimum swing that I can have such that our transistor M1 as well as this current source is in the saturation conditions. Okay. So now in this case one could replace this current source with some sort of transistor being biased in the saturation regime, and this structure we know that it would be drawing a current which is equal to ISS, provided if this transistor has an appropriate width to support that current. Yeah. So what I try to mean here is that let us label this structure that realizes this ISS as M5 transistor, and we know that there is a minimum voltage drop across the drain and the source that has to be maintained such that the transistor M5 is operated in the saturation regime. So this can this ISS can be realized either as a simple structure like this, or it can be realized as a kind of cascode configuration, or whatever the configuration that we have discussed when we discussed about this current mirror can be utilized as a kind of tail current source at this particular point. So in short, this ISS either realized as a simple current mirror, or either being realized with a single transistor or being realized with some sort of cascode configuration, they generally need some sort of drop across them in order to ensure that these structures that realizes this ISS is operated in the saturation regime. And let me label that. Okay, I am not specifically mentioning that this ISS is being realized by just by M5, it can be realized by any other mean. Okay, so but in short, this ISS requires some sort of minimum drop across it, and I label that minimum drop as VCS. Okay, yeah. So hope that you are clear with this. And now whenever we try to have a lower swing across this output node, obviously there is a minimum voltage drop that we have to maintain across the drain and the source of this M1. Okay, so that voltage drop is nothing but our VOV. Okay, so basically it is a VOV1 that has to be maintained plus the minimum voltage drop that has to be maintained across this current source, which is labeled as VCS. Okay, yeah. So this is the expression for our VO max and VO minimum, and these are the two expressions that I can directly plug in into these expression of VO max and VO minimum. But there is something that I have to emphasize here, is that whenever we are observing the outputs differentially, there will be a factor that gets multiplied by this expression, which is nothing but the factor of 2. And the reason for this is that we know that because when we apply an antisymmetrical input, the outputs will also be antisymmetric. So which means that when there exists a positive peak across one of the node, the other node which we label it as VO2, and this node let us label it as VO1. So across this VO1, when we have a maximum swing, the VO2 will be antisymmetric, which means that it will have the minimum value, and the difference between these two would always be doubled when we compare with a single ended structure which has an output swing with reference to a ground. Okay, but in this case there is no reference, so both the nodes are being changing, and they are changing in opposite direction such that they leads to double the output swing. Okay, so yeah, so whenever we have this differential output, in general the output swing would be enlarged by a factor of 2. Okay, yeah. So now let us move on to the next one, where the circuit number B, and let me just try to make some room in order to talk about the output swing of this circuit B, or the differential amplifier with the differential load. Yeah. So this output swing is again can be expressed by VO max minus VO minimum, and since because even this structure is a differential output, so we can directly multiply this factor of 2 when we have this differential output swings at the differential pair. Okay, so now that the only thing that we need to yet to be done is to find the expression of VO max and find the expression of VO minimum, right? Yeah. So again, let us take only one half of the circuit, and whenever there is a positive swing around a common potential, okay. So there is some DC Q point at the V out, and over this Q point there exists an output swing, right. So this output swing can go all the way up towards VDD, but we know that across the drain and the source of this M3 one has to maintain a certain voltage in order to ensure that this M3 is staying in the saturation regime, and that voltage is nothing but VOV3, okay. So the maximum swing that one could have across this Q point, across this output Q point, is written as VDD minus VOV3, okay. And similarly, whenever there is a lower swing, as we had before, the lower swing has to support a minimum voltage drop across this M1 drain and source, as well as a minimum voltage drop across this current source ISS. So due to which one could write the value of this minimum swing to be equal to VOE1 plus VCS, okay. So plug in these two expressions on over here in order to get the total output swing of this particular differential pair with differential output. So now that I just want to compare a differential pair with a single inlet structure, such that we will just complete our review and we will just move on to the next circuit topology, which is telescopic. Yeah, hope that. Yeah, I'm trying to have some room, but somehow, yeah. I think I would rather have the structure or something like this. Yeah. So let me just try to paste the picture that I have copied. Yeah. So again, this is a simple differential amplifier. Or differential pair with single led output, okay. So now again let us look back into those two parameters. One is the gain, the other one is the output swing, okay. So let us begin with this gain expression. So again we know that one could express this V out, or basically the circuit. So whenever we apply an antisymmetric input, we are trying to compute the value of a differential gain here, and whenever we apply an antisymmetric input, obviously we know that this node, since because the circuit is not symmetric, we know that this node cannot be equated to be equal to 0, but we proved just by stating that if at all, if I label this node as x, okay, so this particular node as x, what we have stated is that in order to support a current value of ISS by 2 and a current value of ISS by 2 on both these branches, when we apply a common mode input, we know that this node and this node has to have the same potentials across them, right. And due to which we finally concluded that this node, even though it is not proper to draw a line of symmetry and then directly by inspection I cannot say that this node is at ground, but still with some sort of contradictory proof, we have already stated that this node can be considered as a 0 for this particular case, and then we can analyze the circuit in a normal way, okay. So hope that you could actually recollect whatever we have discussed earlier, and based on this discussion that we have done earlier, I could write that the gain to be equal to the same GM1, 2 plus the output impedance across this node. So again when I look for when we look across the drain of this M4, we have an impedance value which is equal to RO4, and when we look down, we have an impedance value which is equal to RO2. So now let us move on to the next parameter, which is nothing but the output swing, okay. Now again one could write the expression for the output swing as VO max minus VO minimum. The only difference here is that since because the output is taken single ended, which means that the output is measured in reference to a ground, okay, rather than in reference to other node. Here the node that we are taking as a reference is a fixed one, okay, and due to which it is called as a kind of single-ended output structure. And whenever we are having the single-ended structure, the output swing is basically just VO max minus VO minimum, and there is no factor of 2 that has been applied here, okay. So please try to remember this particular point, which is pretty important when we try to solve the problems. Yeah. So now let me write the expression of this VO max again. It is the same expression, just because we have the same similar structure as before. One could write that the value of this VO max as nothing but VDD minus the minimum drop across this drain and source, which would be equal to VOV4, and the next one is VO minimum. Again, when we talk about the minimum voltage, we have to minimum swing at the output, we have to maintain a minimum voltage drop across the drain and the source of M2 as well as the across the current source, which is VCS, okay. So I am just going to consider those two parameters and tie them together as something like this, and plug in these expressions and you would get the output swing expression. Yeah. So now that you could be able to see that this the gain expression is identical to what we have got it for a structure which is labeled as B here. It's the same gain expression, but the output swing is certainly different, right? The output swing that we have attained in this circuit B, where is double the value of what we have got for a single-ended structure, okay. Yeah. So that is something that one has to consider while doing the discussions further, and there is something else that I need to discuss apart from these simple quantities. In short, when you really observe that the node X across this mirror or transistor of M3, this particular node has quite a large hectic amount of capacitance here. Now, why does this capacitance is so important? Because we have already discussed about the frequency response of any structure, and every node in this particular circuit will contribute some sort of pole inside this gain expression, okay. Now we are more focused on this particular node, where the pole that has been created or the pole frequency that has been created is basically falls at lower frequencies. So what it really means is that when you try to plot the magnitude of the gain with respect to the frequency, the pole that is created across this node will generally appears closer to the DC condition. So due to which the 3 dB bandwidth of this entire circuit would then be small, okay, and this is something that one has to consider while trying to use this simple differential pair with a single-ended output structure. Now let me also try to reason it why this particular node creates a pole that is having a lowest frequency in it. The reason, one of the reason here is that the capacitance that has been appearing across this node. So when you look carefully, you could see that there is a capacitance between the gate and the drain of this M1 that adds up to this particular node, and again you would have a capacitance of the gate and the source of M3, the capacitance of the gate and source of M4, and even the capacitance of gate and the drain of M4. So there are a lot of capacitance that are being added to this particular node, and we collectively call this capacitance value to be equal to Cm. And apart from this, when we look carefully here, you could see that the impedance value that we would have across this node will be equal to approximately equal to 1 by Gm3. Yeah. So we know that this pole frequency omega can be returned as 1 by Rc. Now for this node, it can be returned as the capacitance value to be equal to Cm, but the R value that we have is basically equal to 1 by Gm3, and due to which the Gm3 will appear at the top. And we know that the value of this Gm3 is always small, but we also know that the capacitance value is large. So what is happening is that effectively the pole frequency of this is getting reduced, okay. So hope that you are clear with these circuit conditions, and due to which the pole is getting closer and closer to the DC conditions, and due to which the bandwidth of this particular circuit in general will be small whenever we have this kind of mirror structure, something like this, okay. Yeah. So hope that it is clear. So now that we have got enough review to discuss about this telescopic op amp, and let me begin with this different circuit topologies that exist, and among the circuit topology today we will focus on what is known as telescopic op-amp circuit topology. Now as I said, we need to have different circuit topology to enhance the gain of the op-amp, and so I am just going to categorize those circuit topology or basically op-amp topology okay. So let me categorize them into three categories. One is known as a single ended, or sorry, it's a single stage op-amp, and the second one is a two stage op-amp, and the third one is labeled as gain boosted op-amp. Okay. So these are the three major categories I would say, and under this single stage op-amp we have two further subcategories. One is known as telescopic op-amp, and the second one is known as folded cascode op-amp. Okay. So these are the two subcategories that I have categorized under the single stage op-amp. Okay. And the last one, which is known as gain boosted op-amp, is not specifically a type of op-amp. One could actually visualize this gain boosted op-amp as something like a kind of auxiliary device that has been added onto these two amplifiers. Okay. So literally what I am trying to say is that the gain boosted op-amp is not need to be considered as a separate category, but rather it's a kind of enhancement that has been created using auxiliary amplifiers onto these telescopic and folded cascode op-amp to improve the output impedances. Okay. So let me just move on to the first category, which is the single stage op-amp, and specifically we will be focusing on telescopic op-amp configuration. Yeah. And our major focus in all these discussions of circuit topology is to enhance the gain, and while doing so we'll also try to address what are the issues that one would end up having when we are trying to increase the gain of the op-amp configuration, right. Yeah. So now that we know that the gain expression in general, okay, this is not specific to this telescopic, but what I'm trying to say is that the gain expression in general will be always a product of the transconductance times that of the output impedance. So what it really means is that we are talking only about the voltage amplifiers, and these voltage amplifiers can be returned as the transconductance times that of the output impedance. So in all these different circuit topologies, what we will generally do is to improve this output impedance. Okay. And that is what we are trying to do even in this telescopic and folded cascode, even in this two stage as well as the gain boosted stage. Okay. Yeah. So without further ado, let us move on to this discussion of telescopic, and the general configuration of this telescopic is as simple as this. So we already have a differential pair, and we know that one could create a cascode structure for this differential input pair, where I had M1 and we had this M2. So we know that these two structures were basically trying to create a differential input pair for us. Okay. And this is where we fed our input. Now on top of this M1 and M2, what we are trying to do is that we are trying to stack a set of transistors which we called as a cascode transistors, okay, which I labeled as M3 and M4, and it's been biased with a specific voltage of VB. And we have discussed about all these circuit phenomena when we discussed about this cascode op-amp, or sorry, cascode stage amplifiers. Okay. Yeah. So now again we would have this tail current source. Let me just use a different color. and the value of this is basically equal to ISS. Yeah. So now that we have to tap, let us talk about a circuit topology which is differential output. Okay. Yeah. So now that we basically want to have some sort of output to be extracted from the drain of M3 and M4 rather than from the drains of M1 and M2. Okay. And on the top we still have to have a load that tries to mimic these currents. Okay. And we want this current source to be exactly equal to half the value of this ISS. Okay. So let me write it as I1 and I2, and we want this I1 and I2 to be equal to half the value of this ISS that is being drawn by this particular structure. Now the whole point is that let us try to realize these structures with some set of transistors. Okay. So for which let me try to copy this part of it, and let me just move it here. Yeah. So now how one could realize this, just a second. Yeah. So the way to realize this I1 and I2 can be done by just by using a single transistor. Okay. But when we try to mimic this I1 and I2 with a PMOS single transistor, what happens is that let me just try to talk about the a circuit configuration which is a faulty one, and then later I will try to reason why it is faulty, and later I will just try to work on those faulty structure in order to build the real structure that we wanted. Okay. Yeah. So basically in order to realize this I1 and I2 one could use a PMOS transistors, and one can first begin with realizing a single transistors for I1 and single transistor for I2 realization. And we know that when this transistors are being biased in the saturation regime, then they can mimic the value of this I1 and I2, which is basically equal to ISS by 2. But there is a kind of problem that exists in this particular circuit configuration. Okay. And let me label this one as M5 and M6, and let us fix it to some potential like VB1, okay, which is different from this NMOS VB value, and let us fix our VDD. Now the whole point is that when we try to analyze the circuit, one could evaluate the capital GM of this particular circuit just by shorting this node, and since the circuit is symmetric basically, one could draw a line of symmetry, and then in order to evaluate the capital GM one could bring this node to the ground and measure the I out, and once you try to do so we would end up having this current which is flowing across this M1. The small signal current would be driven to the output, and due to which we end up having a capital GM to be equal to GM 1, 2. Okay. Yeah. So this is what we would get after doing all this manipulation, okay, with respect to the capital GM. But when we try to evaluate the value of this R out, that is where we would find that these loads that we have tried to use in the place of I1 and I2, they are not sufficient to create the exact value of output impedance that we are expecting for it. And the reason is that when we try to look down, we could see that this transistor M1 is basically gives us an impedance value that is equal to RO1, and that when it been seen through the drain of this M3, it gets magnified by the intrinsic gain of this M3 structure, and the value that one would get can be written as GM3 RO3 magnifying this factor of RO1, okay, and that is the impedance that one would have when we look down in this across the drain of this M3. But when we look up, the impedance that we end up having is just RO5, and we know that these two impedances go in parallel. So which means that when I put them in parallel, we know that this impedance value is quite small, and effectively what happens is that the impedance value that we would get out of this expression will be approximately closer to the smallest impedance value, which is RO5. So the whole point of stacking this M3 and M4 has been lost, right? So in order to really get the essence, or in order to improve this output impedance across the other end, that is across the PMOS structure, what one has to do is that one has to create what is known as a cascode structure even for this realization of this I1 and I2, okay. So this is the actual structure that one has to do in order to create those I1 and I2 values, and has to bias this uh, M7 and M8 transistors with a particular voltage which we labeled as VB. Okay. So now that when I look for the impedance value of RO7 is being magnified by the intrinsic gain right now. Okay. So this RO7 then be magnified by the intrinsic gain of this M5 when we look through the drain of this transistor M5, and due to which the output impedance can be returned as GM5 RO5 magnifying the drain resistance of M7, which is RO7. Okay. So now that this output impedance is quite larger than compared to the nominal uh, structures when we had earlier, so which is what we had discussed, right? It becomes quite difficult for me to move the pages. Yeah. So in this case we had an output impedance which is just RO3 and RO1, but right now these impedances are being increased quite a lot just by having these cascade structures both across the load as well as across uh, the signal path structures. Okay. So the structures that are composed of M5 to M8 is basically a load, and the structure that is composed or comprised of M4 to M1 is called as a signal path structure. Okay. So we basically have balanced both these structures in order to have an appropriate weight for the output impedance R out. Okay. So hope that it is clear, and now let us try to evaluate the output swing. Now again, since because we are observing the outputs differentially, we know that there is always a factor 2 that sits in front of this VO max minus VO minimum expression. Okay. And now the only thing that is left over is to compute the value of this VO max and compute the value of this VO minimum. Okay. Yeah. So now again, based on this discussion that we had earlier, one could write the value of this VO max as VDD minus VOV 7 comma 8. Okay. Just because I am including the other transistors numbers also, but otherwise if we are considering only one single path, it is just VOV 7. Okay. Yeah. So it is VDD minus VOV 7 comma 8 minus VOV 5 comma 6. And for a lower swing again we have to maintain a minimum drop across this M3, which is labeled as VOV 3 plus VOV 1, and also one has to have a minimum drop across this current source ISS, which is labeled as VCS. Okay. And plug in these two expressions onto this V out output swing expression, and you would get the total output swing. Okay. So this is a case where we have a single where we have a differential output for a telescopic configuration. Now what if you want to realize the same telescopic op amp but with a single ended structure? The structure is pretty simple. I will just try to copy the structure just because it takes some time for me to redraw it. Okay, I think this is actually not helping me. Okay, sorry guys, I'm just trying out few things. Just want to undo it. Let me just try to delete it. Yeah, that would be fine. Let me just try to copy from a different source. Yeah, thank God. Yeah. So now that we have got this structure, and now let us try to and the structure that has been drawn towards the left is the single-ended output of telescopic op-amp configuration. Okay, and the one that is on the right is nothing but the one that I have drawn earlier, which is the differential output for a telescopic op-amp. Okay, so now that let us try to quickly review this single-ended structures gain. Now again one could write this gain expression as by shorting this node to the ground, and what happens is that when you apply an antisymmetric input, since because the circuit is considered to be a kind of symmetric, this VID would then appear as VID by 2 here and minus VID by 2 here, and there is basically these are the gate to source potentials of M1 and M2 that appears, and due to which there is a small signal current across M1 which is nothing but GM1 VID by 2, and across this M2, let me use a different color, there exists a current because of the small signal minus VID by 2, and since because there is a negative sign, the current would direction would be shown in the upward direction, and that value is basically equal to GM2 VID by 2. Okay, yeah. So now just because there exists a current mirror structure that is created with M7 and M8, this current that is flowing across this M1 is being reflected onto this path, and that value would be same provided if we have the same aspect ratio for M7 and M8 and the same aspect ratio across this M5 and M6. Okay, the details of these requirements have been discussed earlier, so I am not repeating them, and as you could see that these two currents would then sum up to a total value of I out. Okay, again when we do all this manipulation, we end up having a capital GM that is equal to GM 1 comma 2. Okay, I am not repeating all these expressions, but I am just trying to say that when we do so, it is the same analysis that we would have used even for a simple differential pair. The same results can be utilized even here. Okay, and the next thing that we have to yet to do is to compute the value of the output impedance, and again the output impedance is as similar to what we have discussed here. So I'll just write down the final result of it. So when we look up, we could see that the RO8 is being magnified by the intrinsic gain of M6, which is GM6 RO6, and that goes in parallel with GM4 RO4 into RO2. Okay, and this is the gain of this single ended structure, and the value of this is exactly same as we had got for the differential structure. Okay, there is no change between the gains, but what exactly the difference that occurs between the single ended output and the differential output is the output swing. So in this case the output swing is written as just a difference of VO max minus VO minimum, and let us try to evaluate the VO max and VO minimum. So the VO max has to ensure that there is a minimum drop across the drain and source of M8 and the drain and source of M6, which and those values are basically VOV8 and VOV6. So due to which one could write that the value of this VO max to be equal to VDD minus VOV8 minus VOV6, and the expression of this VO minimum has to do the same, like it is VOV4 plus VOV2 plus the minimum drop across this current source, which is VCS. Okay, so plug in these expressions onto this output swing expression and you would get the answer for it. Okay, so right now I just want to do a problem based on this telescopic op-amp, and also want to address about the drawback in this particular circuit by using a simple closed loop configuration. Okay. first let me talk about the drawback, and later we'll try to perform a simple amplifier design based on this telescopic configuration. Okay. So in order to talk about the drawback, I just want to bring a small circuit configuration, and let me paste this figure. Sorry. Okay. So here is the case as we had discussed in stream number 2 of op-amp, where we had a unity gain feedback amplifier, and but this op-amp was being realized by making use of a simple configuration, and we found that the output swing, or basically the input common mode range, is basically the same as we had for a open loop configuration of a differential pair, which is a simple structure. Okay. And now in the place of this op-amp, right now we are trying to replace this op-amp with this telescopic configuration. Okay. Now when we have this telescopic configuration, the structure would look something like this. The realization of this symbolic representation is in terms of transistor could be shown something like this here. Okay, this is the transistor level realization of the same structure that is given here. Okay, yeah. So now let us try to talk about the output swing. Okay. Now the moment we had this kind of configuration between the V out and the V in minus node, what is happening here is that let us try to talk about the type of swing that one has to have, such that the transistors M2 as well as M4 are staying in the saturation regime. Okay. So whenever there is an output swing, or whenever there is an input swing, one has to ensure that none of the transistors are moving away from saturation regime, and that is the major goal of this swing that while we try to evaluate it, right. So now what I do is that let me try to talk about the swings that we would end up having when we try to realize this telescopic op-amp as a kind of unity gain feedback circuit. So now with respect to M2, we want this M2 to stay in the saturation regime, and let us try to put upon these expressions, like how the value of VGS with respect to VDS has to be related such that the transistor M2 is staying in the saturation regime. So we know that the drain potential of this M2 can be written as Vy, right. So we want this drain of M2 to be either greater or at least equal to the gate potential of this M2, where the gate is being connected to the V out. So let me write it as VO rather than writing it as V out minus VTH. It is nothing but the VGS minus VT. Okay. So of transistor 2, and let me label this as expression number 1, and this is the condition that we have to maintain whenever there is an output swing, and in order to make sure that our M2 is in saturation regime. So similarly, one could write the same saturation condition for M4 structure as well. So now in this case there is a potential VV1, and that has been related to the drain of this M4, which is nothing but our V out. So again we want this V out to be certainly greater than the value of Vg, which is VV1 minus the threshold voltage of transistor number 4, and that could be written as expression number 2. So now let me rewrite this expression 1 in terms of VO. So which means that I am trying to shuffle some of the expressions here. So VO has to be less than the drain potential plus the threshold voltage of transistor 2. Okay, and let me label this as third expression, okay, which is the derived version of this first expression. So now let us move on to the V out. So when you compare this expression number 2 and expression number 3, both these expressions have a common term, which is V out, so that one could write the total output swing as something like VV1 minus VTH4, and the V out has to be greater than this minimum voltage, and also it has to be smaller than compared to this node potential, which is Vy plus Vth2. Now one can also write the node potential of Vy in terms of Vb, right? So we know that Vy is nothing but it's Vb1 minus the Vgs4. So in a way, Vy in terms of Vb1 can be written as something like this. So one can use this expression in order to substitute over here, such that we end up having a Vb1 minus Vgs4 plus Vth2, and on the other side we have this Vb1 minus Vth4. Okay. So the next thing is that just a second. Now let us try to graph this expression such that one could see that this output swing is very limited. Now in both these expressions we have a common term Vb1, and let us fix this common term Vb1 as some sort of potential, say for example 5 volt or 2 volt or whatever it is. Okay, so we have raised the bar of this Vb1, and from this we have a potential drop of Vth, which is a threshold voltage drop, and so this in turn defines me the Vo minimum level, and the difference between these two is measured as Vb1 minus Vth4. Okay, and this will mark my Vo minimum condition. Now let us mark our Vo maximum condition with respect to the same upper bar of Vb1. Okay, so again one could see that it is a kind of Vgs minus Vth. Okay, so one could write or pull out a negative sign out of this expression, so it can be written as Vgs4 minus Vth2, and which is nothing but it's almost closer to the value of VOV, even though the transistor threshold voltage of 2 and we are making in connection with VGS of M4, they are actually not appropriate, but still one could visualize this VGS minus VTH as something like VOV, and we know that the value of this VOV can be made smaller than the value of VTH. Okay, so if that is the case, we end up having a difference. Okay, so VB1 minus the small VOV would end up having a particular value here. Okay, just because I am drawing this by a very small quantity, and the difference, the height difference between these two is written as VB1 minus some VOV. Okay, so VOV4, let me write it, okay, and that is the swing that I have, and this would mark my VO maximum condition. Now clearly you could see that the amount of swing that I have left over is only between these two regime. So any swing has to be well within this difference between this VO max and VO minimum. If you go beyond this particular voltage, trying to move away from this swing, away from this defined value of VO max and VO minimum, then obviously the transistor M4 or M2 will move out of saturation. Okay, so clearly there is something that one could visualize, that the amount of swing that one would end up having is very limited when we go for a telescopic configuration that has been used to realize as a unity gain feedback. Okay, so the final conclusion that one could have is that one cannot use a telescopic op-amp configuration to realize an op-amp that is used in a unity gain feedback. Okay, so that is one of the major drawback that one would have here. I hope that you are clear with it. Okay, so now let us try to leave this drawback as it is here, just because I will just use this drawback in order to create an idea for this folded cascode op-amp in the next video. But as of now, we'll just hold this drawback in our mind, and let us do a simple problem based on this telescopic configuration. So let me try to copy the problem. Okay, let me undo this. Let me try to paste it as a picture. No option. Yeah. So again, I'll just try to talk about this particular problem. Yeah. So you have been asked to design a fully differential telescopic op amp. So among these two type of op amps that we have discussed for a telescopic op amp, the configuration that is being asked here is a fully differential. So what it really means by a fully differential is that the output has also been taken as a fully differential. Okay. So the configuration that we are talking about fully differential is this, not this circuit that is given towards the left. Okay, it is this circuit that has to be realized. Okay. So you need to draw the circuit complete picture of it in order to design this particular in order to solve this particular problem. Okay. So when you are being asked to design, you have to draw this entire circuit setup, and when it has been set as fully differential, one has to have a differential output swing of this telescopic op amp. Okay. Yeah. So hope that you are clear with this. And the next thing is that we have some set of data that is being given. The very first data that is given here is the supply, which is VDD, and there is also the output swing. The differential output swing is being given, and the power dissipation is given, and along with the gain, voltage gain is all being given. Okay. Yeah. So now what we will do in this case is that let us try to assume that the circuit has been designed, has been drawn by you, and I'm not going to spend much of my time in drawing this same picture, but rather I'll just take a copy of this figure. We try to paste it here. Yeah. Yeah. So specifically for this, solve this problem, the very first thing is you need to draw the structure, and assuming that you have already drawn the structure, let us move on to the solution part. Now there are basically some 4 steps that are involved in solving this particular problem. Okay. Now because we don't know what is the DC current that is flowing across the circuit, the data that one could look for evaluating the DC condition is this VDD as well as the power dissipation. Okay. But there are certain cases where in case if there is a data that is given as slew rate, so it is only the slew rate that defines the current in an op amp. Okay. So obviously here in this particular question, the slew rate is not being specified, and due to which one could use this power dissipation data in order to evaluate the DC current flow through the circuit. Okay. So now the DC current, or basically the step number 1, is to evaluate the DC current or the bias current. Okay. Yeah. So we know that this power dissipation can be returned as a product of VDD, which is the power supply, multiplied by the biasing current, which is I bias. Okay. Now we want the value of this I bias, and where it can be done by a simple way, just by dividing 3 divided by this 10 milliwatt will give us a current value which is equal to 3.33 milliamperes. Okay. Now we are going to split this 3.3 milliamperes of current into 2 segments of currents. Okay. So one part of the current will be used for biasing this reference sources, okay, which is basically need to fix the bias voltage of M7 and M8 as well as this M9 structure. Okay. So we will dedicate this 0.33 milliamperes of current in order to realize these I references. Okay. And we will use the remaining part of the current, which is basically 3 milliamperes of current, in order to realize this entire structure. We assume that the entire 3 milliamperes of current is flowing through this M9 transistor. Okay. And that is what we have evaluated right now, and let me write it as for, and it's been used for the op amp circuit condition. Yeah. So now the one thing that we are really concerned is that we have to evaluate the W by L factors, which means that in order to evaluate a W by factor for each of these transistors that are given in this circuit, we have to know the DC current condition along with the other data which is known as the VOE value, okay, because we assume that each of these transistors that are drawn here is all operated in saturation regime, okay. So from the saturation current equation, we know that one has to know the W by L factor, or one has to know the current that is flowing, and the other data that is required to be known is the VOE value. Now once if we know both these values, then one could evaluate the W by L factor for each of these transistors, right. Yeah, so the next step that we are going to do is to find a way by which we can get the value of VOEs for these transistors. Now when we look carefully, so let me write this as step number 2 is to evaluate the overdrive voltages for the transistors, okay. So now the data, so which data can be used for evaluating the VOE value in this case is by looking at this particular data that is given, okay, the differential output swing data. So now let us utilize this data in order to evaluate the VOEs of all the transistors that are given. Okay. We know that the output swing, since because it's a differential output swing, we know that this expression of output swing can be written as 2 into VO max. So again I will plug in this expression directly. VO max is nothing but VDD minus VO 7 comma 8 minus VO 5 comma 6 minus the VO minimum swing, which is again these VOEs, so which is written as VOE 3 minus VOE 1 minus the VOE of 9, okay. Yeah, so now the output swing that is given is equal to 3 volt, and here there is a factor of 2. So when we divide this factor by a 2, then we end up having a result which is 1.5, and inside this expression the value of VDD is given as 3 minus this whole expression. So probably I will just try to copy this expression. Okay, yeah. So again after doing a simple algebra, one would end up having a kind of result which looks as VOV or VO 7 and VO 5 plus VO 3. So there is no need of modulus for NMOS VOVs, so I just remove the modulus, and VO 9, and that is equal to 1.5 volt. Yeah. So now in this case we know that the transistor M5 as well as this M7 carries the same current, right, and if we assume that the VOEs are same for both these structures, then one could add up these two to a single value which is equal to VOE 7, okay, so twice the value of this VOE. And similarly, since this M3 as well as the M1 carries the same current, one could combine both these values to be equal to twice the value of this VOV 3, okay, plus there is a VOV that has to be assigned for. Now we know that the sum of these values is supposed to be equal to 1.5. All the VOEs has to be summed up to a value of 1.5. Now what value to be assigned for each of these unknowns? Now again when we look carefully into this question, there is a data that is given that the output common mode value is supposed to be equal to 1.65. So which means that when I try to measure this output DC condition, the node value is supposed to be equal to 1.65. Okay. Now over this node there is an output swing. Okay. So if I consider only one single branch of it, a single branch will have a total swing of 1.5 volt. Okay. It's not been doubled. So the doubling will happen only when we try to measure the output swing with respect to the other end. Okay. So only then the factor 2 will come into picture, but in case if I am not considering the factor 2, then the total swing that I would have across a single node, say for example X node, will be equal to a peak to peak swing of 1.5 volt. Okay. hope that it makes sense. So which means that one could have this 1.65 as the mid value, and the total swing is happening around this mid value equally, which means that the magnitude of this top swing can be returned as 1.65 plus this swing, which is half the value of this 1.5. Okay, and similarly one could write the expression of this VO minimum as 1.65 minus 1.5 divided by 2. Okay, so we are actually dividing this total swing of 1.5 into two halves, and then they are being added on to the base of 1.65 in order to get the value of VO max as well as VO minimum. Okay, hope that it is clear from here, and we'll just try to write down these values right now. So this value turns out to be equal to I don't have the calculator. I think 0.75. So yeah, so we end up having a value which is equal to 2.4 volt for the topmost swing, and for the bottommost swing it is a subtraction that has to be done. So that would end up having a value which is equal to 0.9 volt. Okay, so hope that I'm right with the data. Okay, so the minimum swing that we would have supposed to be equal to this 0.9 volt. So what we really mean here is that the summation of this quantity supposed to have a value which is equal to 2. Sorry, I think I'm just missing out. Yeah, so it is 2.4 minus 3 volts supposed to give us this quantity. Maybe I have to plug in these data over here. So this is happening at 2.4, and the maximum swing that we have is equal to VDD, which is equal to 3 volt. So the difference between this topmost swing and this value of VDD is being dedicated as the VOEs for both these transistors, and those VOEs has to sum up to a value which is equal to 3 minus 2.4, which is equal to 0.6. So what does it mean is that the summation of this quantity is supposed to be equated to a value which is equal to 0.6 volt, whereas when we consider the remaining part, okay, which is 0.9, this 0.9 volt has to be summed up across these VOEs. So in this we know that this transistor M9 carries most of the current, which is double the current. So one would dedicate a large value of VOE for this, otherwise the WL factor of this M9 would become so large, and due to which what we would do is that we will split this 0.9 as 0.5 here and 0.4 here, so that they both add up to get a value of 0.9 volt here. Okay, so now that based on these discussions, let us try to write the VOE values. So VOE 7 is basically equal to 0.3, and even our VOE 5 will also be having the same value, and the VOE 3, also VOE 1 will all have a value which is equal to 0.2 volt, whereas the VOE of 9 will have a value which is equal to 0.5 volt. Okay, yeah. So now that in step number 2 we have evaluated all the VOEs based on different circuit conditions, we have got the values of VOEs, right? Yeah. So the next thing is that we just have to calculate the WBL factors, and also we also have to ensure that the gain that we are getting supposed to satisfy the gain requirement of 2000. Okay, so there are 2 more steps has to be done in order to complete the design process. So let us move on to the step number 3, which is the calculation of device dimension. Now we know that just by using the simple formula of current, because we know all the transistors are operated in saturation regime, based on the saturation current expression, one could write it as mu COX times that of VOV, okay, the whole square. So based on this, one could evaluate the value of WL factors for all the structures that we have discussed till now. Okay, so I will just give this as a part of an assignment. You can just try to work out for all the WL factors of the transistors that are given here. Okay, so right from M1 all the way to M9. So we have to apply appropriate values of VOEs and appropriate values of the current flow and the appropriate values of mu n COX or mu p COX values in order to evaluate the PMOS and NMOS aspect ratios. Okay, yeah. So after doing this, the last step is to verify the gain of the circuit. Now the gain of this particular circuit is written as GM1, 2, and we know this gain expression is already been discussed. So I am just writing only the result of it. Yeah. So now when we try to in order to evaluate the values of GMs and R naught, we have to have like in order to calculate the value of GM, one could use this K n dash W by L, or since we know the values of ID and VOVs, one could use this 2 ID by VOV formulae to evaluate the GMs. Okay, but for the calculation of R naught, we have to know either VA or the early voltage or the lambda value. Okay, so and the current. So basically we have to see what data is being given in the question, and let us look back into it. I guess the data of lambda is also given. Yeah, since the data of lambda is given, one could use this lambda value to evaluate the small signal impedance value across the drain just by having this 1 upon lambda times that of ID. Okay, yeah. So now what basically would happen when you try to evaluate all these quantities is that when you do the calculation, you will find that this particular quantity, which is basically the output impedance when we look towards the PMOS structure, seems to have a value which is equal to 111K. Okay, whereas the NMOS structure will have a value which is 667 kilo ohm. Okay, so just because we have a very small impedance on one end, whereas the other one is almost like 6 times higher than the impedance that we have got from the PMOS structure, it leads to an imbalance in the output impedance, and due to which when you try to evaluate the gain obviously ends up having a value which is equal to 1426 volt per volt. Okay, and this is a value which is way smaller than the gain expression that is being asked to be done, right? The gain that is being asked over here is to ensure that the gain of this particular circuit has to have a minimum voltage gain of 2000, but what we have got as of now is a gain value that is even lesser than this 2000. Yeah, so now what could be done in order to improve the gain? The way that one could improve the gain is by looking at this differences in the values. Okay, you could see that there is an imbalance between the output impedance of PMOS branch and the NMOS branch. So we certainly have to improve the output impedance of this PMOS branch, and we know that the factor lambda, as I said, the lambda can be written as something like lambda prime divided by L. Now when we look carefully, the value of this lambda n is basically equal to 0.1 volt inverse, but the value of this lambda p is basically 0.2 into like a volt inverse. Okay, so this particular factor is the most important factor that has reduced the value of R naught, just because it has been divided by a factor of 2 when we compare the output impedance of R naught for an NMOS. Okay, so there is a difference of 2 between this lambda n and lambda p. Now since because this lambda n or lambda p is basically proportional to the length of a transistor, let us try to increase the length of the PMOS. Okay, so I'm talking about only the increase or doubling the length of the PMOS transistor. When we do so, what would happen is that this would end up having a value of lambda p, which would then be equal to a value which is equal to lambda n. Okay, this becomes 0.1 volt inverse. Okay, but when we do so, when we try to improve or when we try to double only the length of a PMOS transistor, obviously the GM will also get modified, right? The GM is basically is proportional to WL factor. When we use some other expression, we know that it is proportional to WL factor. So when we try to just increase the length of the transistor, then obviously the GMs of all the structures that we had will also be reduced by half. But we don't want to change this GM value of these transistors. So in order to how to say, so in order to not to change the GMs, what we can do is that we can also try to multiply the width by the same factor 2, so that both these factors would then cancel each other, and we end up having a GM value which is not changed when we try to increase the length of the PMOS transistors. Okay, yeah. So hope that you are clear with us. So now, based on this expression, when you try to recalculate this this PMOS output impedance, you would end up having a value which is almost closer to 600 kilo ohm. Okay, and due to which we will have a gain which is more than 2000. Okay, yeah. So I would advise you to complete this calculation and try to evaluate by yourself, and probably I'll be continuing this video in the next class with the introduction of folded cascode op amp. Thank you.